My name is Alexander Krizhanovsky, and firstly, let me start from how did we come to kernel TLS handshakes. Actually, we are a custom software development company, and we had a project in 2013 to develop the core of application um, web application firewall. Web application firewalls are typically based on some open source HPS accelerator like HA proxy or Nginx, and they do a lot of security checks to block web attacks and L7 DDoS attacks. That time we realized that while Nginx and HA proxy servers are perfect HTTP servers, they were never designed to filter out massive malicious traffic like web attacks, like password crackers, for example, or 7 DDoS attacks also targeting HTTP layer. So we thought that, well, if we have HTTP IP tables or nav tables on TCP IP layer, why not to continue the stack with HTTPS protocol and get HTTP filter on top of it. So we started to develop Tempesta FW, which is actually a hybrid of HTTPS accelerator and firewall, and it's directly embedded into the Linux TCP IP stack. Tempesta TLS is a part of Tempesta FW, and Tempesta FW were considered as open source alternative to application delivery controllers. Application delivery controller in this context is HPS accelerator, which also makes additional checks, for example, to block DDoS attacks, provide SSL offloading, load balancing, block web application attacks, and a lot of other functionality. Typically, the most strong players in the market are F5 Big IP and Fortinet application delivery controllers. They are hardware appliances, and Tempesta FW is considered as an open source alternative to hardware appliances. So you can use community server with Tempesta FW and get roughly the same performance and features 5 Big IP or Fortinet. If you look into the technical specs for the appliances, then you always see TLS connections per second or transaction per second. This is very important factor, and we put additional attention to TLS performance. So we come to Linux kernel TLS handshakes. Besides the fact that moving to kernel provides you additional performance because there's no context switches, no copying, less socket overhead like file descriptors and so on. This is also good point about security. So if we move all the security stuff and all the security sensitive data like session keys or private keys to the kernel, the trusted address space, which is very slowly evolving, and leaves all the application logic to user space, application level. For example, content delivery networks always do something with Nginx. There are a lot of patches on top of mainstream Nginx, which are required only for this particular CDN. So if you have a user space application level logic, which is quickly evolving with custom patches, there's high chances to introduce bugs or even security vulnerabilities. So in this case, it's always good to have all the security sensitive data inside the kernel, the trusted address space, and separate that from a probably vulnerable application level. And this approach is actually used by Varnish. Varnish separates TLS termination in each daemon, which is separated from main Varnish processes. And also Cloudflare uses Nginx on their on part of their service just for TLS termination, and completely different Nginx instances for application level. And this architecture allowed Cloudflare to survive Cloudbleed. During that attack, no any security sensitive data were leaked. In this presentation, I'll be focusing on NIST P256 elliptic curve because it's the most popular in TLS handshakes. This much faster 25.519 elliptic curve. However, the curve isn't allowed for certificates. Certificates can be signed only with RSA or NIST curves. RSA is much slower than elliptic curve. The elliptic curve 521 isn't recommended, and the elliptic curve P384 is just slower than 5 to 56. So NIST NIST 256 is the most popular, and it's mandatory for any TLS handshake. Now, if we look on perf profile for OpenCell and Nginx under massive TLS handshakes, then we see that while cryptography is expected bottleneck for the handshake, the cryptography is in blue on this slide. The actual bottleneck is about various memory allocations, copying, and so on. All the stuff is selected by red on the slide. So in Tempesta TLS, we used MBTLS as a foundation. So we forked from MBTLS 2.8. We made a lot of work to make it much faster. We used a lot of our own mathematics and implementation. And also we borrowed some logic from WolfSL, very fast open source implementation. And during that work, we also reported a security issue for WolfSL. I will talk about this report a bit later. All the cryptography implementation have their embedded performance benchmark tools. These are numbers from all the benchmarks for OpenCell, WolfCell, and Tempesta TLS for elliptic curve operations, the CDSA and the CDHE. WolfCell is faster than OpenCell. However, the direct comparison with Tempesta TLS would be fair, because in Tempesta TLS we use full mathematical operations required for TLS handshake, not just basic multiplications for scalar on point for OpenCell and WolfSL. So let's make a demo. In this demo, I will use Tempesta TLS and two Nginx builds with OpenCell and WolfSL. I will use TLS 1.2 because currently Tempesta TLS supports only 1.2. I will use full handshakes and abbreviated handshakes. Abbreviated handshakes is a type of handshake which you usually face when you return to the same website. For example, when you have a TLS ticket for our previously established TLS connection. This measure is very frequent. Next, I will use our own open source performance benchmark, TLS perf. It's basically just do a lot of TLS handshakes using Open SSL to a target server. So let's switch to terminal. Now we see it and start from TLS connection to Nginx with OpenSSL. What's going on here is that we use the cipher suite for elliptic curves. Next, we see prime. This one is, this one for WolfSL. Next, I use 2 threads on this machine and run the benchmark for 10 seconds. This abbreviated handshake since I use tickets on option. The current machine also this 2,000 connections produced by the benchmark to the target server. All the servers are running in single CPU virtual machine, and now I use task set CPU list to use a separate 2 cores for the benchmark. So let's analyze the results. The first one is OpenCell with Nginx. This Wolf SSL, Wolf SSL is about 2 times slower, and this for Tempesta TLS, it's almost 3 times faster for both of them. In this particular case, we also see that tail latency for all the measurement in all the tail latencies, Tempesta is shows much better numbers. Next, use the same benchmark with full handshakes. Okay, we're done. So in this case, Wolf SSL faster than OpenSSL. Tempesta TLS is even faster than both of them. Roughly 2 times faster than OpenSSL and about 50% faster than Wolf SSL. Let's switch back to the presentation. If we compare the numbers with what Big IP and Ivy Vantage, another proprietary vendor, proposes for TLS handshakes, then we observe the second thing, the following thing. First one is that you can watch the performance benchmark between Big IP and Nginx running on top of F stack, which is DPTK-based FreeBSD TCP/IP stack, and comparison of Big IP with Nginx running on top of DPTK. In this particular case, there's no sense to run to measure Nginx with OpenCell on top of DPTK because the bottleneck is OpenCell, not the network IO stack. In that benchmark, Big IP could provide only 50% better performance than OpenSSL. In case of Tempesta TLS, we just saw that Tempesta TLS can provide about 2 or 3 times faster, better performance than OpenSSL. And also, Vantage, basically, this depends on particular CPUs. I guess that particular CPUs for Vantage was pretty old, but roughly Vantage provides the same TLS handshakes performance as basic OpenSSL. By the way, Big IP uses their own TLS implementation. This is why they're faster than OpenSSL. So why our implementation is faster? The first one is technical things, just no memory allocation, no context switches, better IO, less message queues, and so on. You can find details about that performance improvements in our NetDev talk, but also we use different cryptography mathematics. And let's deeper into the mathematics, what's different in our implementation from OpenSSL. Let's consider the basics. So we work in NIST 256, we work in a finite field defined by prime. This prime is a special form. It means that this prime has zero parts and all the parts of 1 bits. The special form of the prime will be important for us on later slides when we'll talk about modular reduction. Next, we have basic operations like negative operation, summing, and doubling. The most fundamental operation in elliptic curves is point multiplication by scalar. In CDSA, we have a known constant point and use scalar as a secure random. In CDH, we use different point, which is actually a public key, and we use scalar as a private key, also secure value. Next, consider what is point multiplication by constant. In the most trivial case, point multiplication by scalar is just a loop over all the bits of the scalar. So we iterate over each of the bits and double point on each of the bit. If current bit is 1, then we add a point to the current result. This is very straightforward, what we actually do with any multiplication even in scalar. Next, if we have a fixed point, as we have in the CDSA algorithm, then we can make some precomputation and run the point multiplication much faster. Also, in ephemeral case with elliptic curve Diffie-Hellman, we also use constant point multiplication for new keys generation. So in total, in those in each TLS handshake, we have two multiplication of scalar on a known point and one unknown point. This is why we saw that benchmark tools for Tempesta TLS showed lower numbers than OpenSet and WolfSet because we use additional unknown point multiplication. Next level is that since we talk about points, the points are defined in some coordinate systems, and default affine coordinates isn't the only one possible and isn't the fastest one. The most implementation work with Jacobian coordinates. Jacobian coordinates allow us to run much faster point additional and point doubling. In this slide, we see formulas for point addition and point doubling for Jacobian coordinates, which has much better estimations than point addition and doubling for affine coordinates. The estimations are defined in m's and s. M is multiplications and squaring. As lower number we have, the better estimation is. Also, besides that, Jacobian coordinates are more efficient. This overhead to make a transition from one coordinate system to another. So if we have a long computation, then it does make sense to introduce the overhead for coordinates transition and run much faster. If we use very small computations, then it's better to stick on affine coordinates. This example of point addition in Jacobian coordinates. This is a formula which employs several sophisticated mathematical operations like subtractions, powers, multiplication, squares, and so on. In total, we can estimate this as 11 multiplication and 5 squares. We usually, in mathematical estimation, we use the most important multiplication and squaring as much more expensive operations than subtractions and additions. So this formula takes 11 multiplications and 5 squares. Usually next we can estimate all the operations in solely in multiplications and consider squarings as about 80% from multiplication. This is true for Montgomery model reduction, but for FIPS model reduction, squares takes as much as 90% of multiplication. Next, model inversion is one of the slowest operations which we need, and it usually estimated as 100 multiplications. All the operations are done with modular arithmetics. This example for modular arithmetics in prime field with prime 29. And on the right side of all the equations, we see positive numbers from 0 to 28, including 28. Montgomery reduction is most used to know the implementations. And the only reason why we have a FIPS reduction on this slides is because MPTLS originally used these types of reduction. It's pretty slow, and we made our best to apply all the recent research which we could find to make the reduction faster. And our best results was 65% slower than Montgomery reduction. The high-level idea of Montgomery reduction is to replace model reduction with prime to model reduction with the power of 2, which is much simpler and fast operation. So we choose high power of 2. The first actually this is the first power of 2 right after our prime. In our case, this 2 in the power of 256. Next, we replace our operands, in this case A and B, by multiplication by this large power of 2 and reduce them by our prime. And next, we since we made a transition from Montgomery to Montgomery domain using this multiplication and model reduction, next we can run the bunch of mathematics operations with very fast reduction by power of 2, which is very fast. And lastly, we need to convert the resulting number back from Montgomery domain to our original model reduction model domain. Again, this is very fast if we have a lot of mathematical computation and we and the overhead for transition to Montgomery domain becomes negligible. However, if we need only several mathematical operations, then probably it makes sense to stick FIPS model reduction. So at this point, we have several layers of mathematics. At the top level, we have a point multiplication by scalar. Next, we have different formulas for point doubling and point addition. And at the last point layer, we have different versions of model reduction. In general, we need to find the balance between all the layers to make the as fast as possible implementation. To make it more clear, let's consider an example. Consider we employ a more efficient point multiplication by scalar, which needs only 52 point additions. This is much better than we saw for original naive implementation, which in average requires 128 point additions. Next, if we use Jacobian coordinates, we pay 11 multiplication and 5 squaring for each addition. However, if we move to mixed coordinates, I think Jacobian, then we can move slightly faster as 8 multiplication and only 3 squares. However, at this point, we need to go to, if we need to go to affine Jacobian coordinates, then we need to make a coordinates normalization twice. And in this normalization, we need a very slow modular inversion. So if we use basic modular inversion used by all the implementations, then there's absolutely no point to use affine Jacobian coordinates. However, in our work, we used the recent Bernstein formulas for point inversion, which is much faster. So in our case, affine Jacobian coordinates can run as fast as Jacobian coordinates. We didn't get much performance in this formula, but at least we use fast inversion. However, if we move it to Montgomery arithmetics, now inversion model inversion becomes also faster, and all the computation, including the transition to affine Jacobian coordinates and all the multiplications, became faster. And now we get 28 performance improvement for elliptic curve Diffie-Hellman and 6 performance improvement for TLS. When we talk about performance, it's very important to not to forget about security. One of the interesting security aspect of cryptography implementation is side channel attacks. With side channel attacks, an attacker usually can evaluate the time spent by implementation for mathematical computation. We saw that the original algorithm for point multiplication by scalar used a different number of addition depending on the input data. So by evaluating the time required for mathematical operation, an attacker can estimate and reveal the actual secret key. So there are three main approaches which are used in implementation and research. The first one is constant time algorithms. Basically, all the implementations like OpenCell, WolfSSL, and BTLS use constant time algorithms. Next, point randomization. Only BTLS uses point randomization plus 2 constant time algorithms. Dummy operations are used with non-constant time algorithms to introduce additional dummy operation to make the computation time constant. Actually, I don't know any existing implementation using dummy operations. In Tempesta, we can use point randomization or constant time algorithms. With point randomization, we can use very fast algorithms. For example, model inversion can be 3 times faster. The good news is that modern CPUs provide RD-rand instruction for random numbers generation. The bad news is that there were SRBDS attack, and the mitigation of the attack costs about 97 performance. And actually, there's no point to use the instruction at all. But another good news is that the recent version of Intel CPUs fixes the issue. And now if you trust Intel, you can use random number generator. But this, again, up to you. You can compile the code with random point point randomization or with constant time algorithms. The next thing about side channel attacks is CADSA, which uses pre-computed table. Usually this table is very big. In WolfSSL and OpenCell, this is about 150 kilobytes, which is much larger than layer 1 data cache. It means that if you access the table frequently, then you observe cache misses. And the cache misses actually generates the different computation time for the whole operation. And now we, even if we use constant time algorithm, thanks to data access, the time isn't constant. So OpenCell scans the full table for each access, and WolfSL used direct access. And that was our original report for WolfSL. And now they use full scan just as well as OpenSSL. The last thing is that all the implementation use big integer arithmetics. For NIST 256, this 256 bits arithmetic, which is for 64 bits integers. The 450-bit integers are called limbs. And this is a good book from Tom Dennis about basics of big integer mathematics. And the most reason why MBTLS was so slow is that they overuse the generic MPIs. However, all the implementations like WolfSL, OpenCell, or Tempesta use specific assembly implementation for all the arithmetics of different sizes. Let's have a this is just a fun comparison of C and assembly code. And if you can see the addition of two limb integer, 128-bit integers, then we need to first, in C code, we first need to add the less significant limb and compute the carry. And after that, make addition of the most significant limbs with carry. This is just 3 lines of code, but the code isn't so trivial. Probably you need some time to make sure that carry computation is actually correct. However, if we move to assembly, we don't not only need to conditional statement, but also we use much simple computation. And actually, x86-64 architecture provides us instruction add C, which uses carry bit. So using the native carry bit computation of the architecture, we can write not only faster code, but also simpler code in assembly. This is why most of the implementation just use plain assembly implementation for all the maths. So we almost done. Let's just talk about the future to-dos. At the moment, the recent architecture provides AVX 512 extension, which have almost no downlocking. So now it does make sense to try the extension for even faster vector computation of large mathematics. Next, we are going to upstream, and at the moment we're communicating with the NFS development team who develops the new standard RPC over TLS. And this standard NFS file system will use TLS encrypted traffic. So we suppose that this subsystem will be the first user of our kernel TLS handshakes. Besides the NFS, we supposed to provide user space API, just like current KTLS. So any servers like Nginx or HA proxy can benefit from faster TLS handshakes. We also need to implement TLS 1.3 because at the moment we have only 1.2. And also at the moment we have only server-side implementation, and in that time we will need client-side as well. There are details about this effort on NetDev Talk, and this also our issue 1433, which describes the design for the user space API. This, besides moving to kernel upstream, we also plan to improve some Linux kernel cryptography. For example, hashing of SHA-256 is about 30 to 100% slower than OpenSale, and it can be improved. And also there are additional copies, necessary copies for KTLS. You can find more discussions about Tempesta TLS development in our NetDev papers and talks by these links. And now I'm done. We appreciate any support and any donations for the TLS upstream, kernel TLS upstream. At this moment, our website is running under Tempesta FW and Tempesta TLS, so they are actually usable. So I'm done. Thank you.